Hey everyone, it's Billy Carson, aka Forbidden Knowledge. I have an amazing guest today, Professor Avi Loeb. Now, Professor Avi Loeb is a well-distinguished gentleman. He received a PhD in plasma physics at the age of 24 at the Hebrew University of Jerusalem. And he was subsequently a long-term member of the Institute for Advanced Study in Princeton, where he started to work in theoretical astrophysics. In 1993, he moved to Harvard University, where he was tenured 3 years later, and he is now the Frank B. Baird Jr. Professor of Science and the former chair of that department. He also holds a visiting professorship at the Weizmann Institute of Science and is a senior professorship, which was given to him and appointed to him in the School of Physics and Astronomy at Tel Aviv University. Mr. Loeb has authored 1,000 research articles, which I've read a lot of those, and 8 books. Welcome to the podcast, Mr. Loeb.
Thanks for having me. It's a great pleasure to join you.
Yeah, and so it's been, talking to you has been a dream of mine for a very long time, I'll tell you that right now, because I've watched a lot of your work, I've read a lot of your research papers, even before Oumuamua. And so I've known about you for a very, very long time. So it's an honor to have you on the show and to be able to talk about some of these amazing topics. And I know that there are people in my community, that you have some conspiracy theorists and you have some conspiracy fanatics. And the reason why I like talking to people like yourself with real hard credentials is because we can clear up some of the information and add some legitimacy to the things that we're talking about by talking about real scientific facts and not fiction and these crazy, sometimes a lot of crazy ideas. So I just want to touch base. We're going to have a great conversation today, and I want to ask you a few questions about things that are already really in your wheelhouse, things that you know about a great deal. But first, I want you to tell the people, what got you interested in astrophysics and why did you get into this field?
Yeah, in fact, as a kid, I grew up on a farm and I was very interested in philosophy, the basic questions about our existence. And I was born in Israel and therefore had to serve in the military at age 18. And the closest thing that I could find to philosophy was doing physics, because that can be used for applications that that society values as part of my service. And as a result, I finished the PhD in physics and then was offered a fellowship at Princeton to study astrophysics. I didn't really know how the sun shines. And one thing led to another. I ended up at a tenured appointment at Harvard University and became the chair of the astronomy department. But all along, I had this sense that it's an arranged marriage. But after a while, I realized that I'm married to my true love, because we can ask fundamental questions about the universe and address them in a scientific way. Now, what do I mean by scientific? I mean, we should pay attention to what nature tells us, to evidence, to data, rather than having our own opinions. Because if you look at human history, people were very often, compelled to argue that we are important, that we are the center of the universe. It ended up that we are not at the center. I mean, the Earth moves around the sun moves around the center of the Milky Way galaxy, which is 1 out of a trillion galaxies in the observable volume of the universe. So we are not at the center of stage. And moreover, we just came to exist. The Homo sapiens, the human species, came to exist only a few million years ago. And that is just one part in 10,000 of the age of the universe, And so if you arrive to a play, in this case, the cosmic play, you are not at the center of stage, and you're coming only at the end of the play. The play is not about you. That's a very simple message. Right. And most people refuse to accept that. So the argument now that we know that we are not at the center of the world is that we are the only sentient species out there, that we are the most intelligent. I mean, we know that we are probably the most intelligent here on Earth, and even that is going to change with artificial intelligence. Within a decade or so, there will be systems more intelligent than we are. But it's, I think, very arrogant of us to believe that we are unique and special, that Albert Einstein was the smartest scientist who ever lived since the Big Bang, 13.8 billion years ago, because there are tens of billions of stars, just like the sun, in the Milky Way galaxy alone, in our own galaxy. And a significant fraction of them have planets like the Earth. So I think it's actually more natural to assume that we are mediocre, that we are sort of in the middle of our class. And that there were, and most stars formed billions of years before the sun. So it's very likely that another civilization predated us. And we can learn from them. We can learn from their mistakes, from their history. You know, if they ever reach us, if they send probes that are in our neighborhood, you know, they must be more advanced than we are because we never reached their doorstep. So altogether, it offers an opportunity. And, you know, that's why I think we should be humble. We should be modest. And most importantly, we should not pretend to be the adults in the room, because most people just have an opinion on this subject. They think they know the answer. But the way kids operate is really the right approach. We should just look around, check without any prejudice, and figure out who is out there. And if we have a neighbor, you know, it could change our perspective about our existence, because we know that finding a partner in our daily life can give a meaning to our existence. And so if we find a partner out there, you know, it will change everything, because we will not feel lonely anymore. We could ask them for answers to questions that we haven't found the answers to. And, you know, the Nobel laureate, Steven Weinberg, wrote a book called The First 3 Minutes. And at the end of it, he said, the more we understand the universe, the more pointless it looks. And I say it looks pointless to most scientists because they are focused on lifeless entities like stars, elementary particles, you know, things that do not have life in them. If we find another intelligent civilization, I think we might find a meaning to our existence out there.
Yeah, that's so powerful. And that kind of takes me back to one of the questions I was going to ask today about the Kardashev scale. Can you elaborate on that a little bit?
Yeah, so the Kardashev scale is based on a scale devised by a Russian astronomer who said that a civilization can be gauged in terms of how advanced it is based on the amount of energy that it extracts from its environment. So, for example, at the very best, you know, we are attempting to extract as much energy as the Earth is intercepting from the sun. For example, when people talk about clean energy using solar panels, you know, there is a certain amount of sunlight that the Earth intercepts. And even if you cover the entire Earth with solar panels, you will get just 1 part in 100 million of the energy output from the sun. The sun is a nuclear reactor held by gravity, basically fuses hydrogen atoms and generates energy this way. You can think about it as a furnace. But we are located very far away. The Earth is small, and it intercepts a small fraction of the energy output of the sun. So you can imagine a more advanced civilization that would surround its star with a megastructure that would harvest most of the energy coming from the star. So that's a higher level civilization according to Kardashev. And then even beyond that, you can imagine maybe a civilization that uses the energy of many stars, maybe the entire galaxy. So that's a higher level of civilization. That's the way Kardashev defines civilizations, based on how much energy they harvest from their environment. I have a different view. In my book, Interstellar, that just came out a few months ago, I discuss a different way to evaluate how advanced the civilization is, and that's based on how it interacts with its environment. In other words, how it shapes the environment. So, you know, the worst you can do is basically use up whatever nature gives you, and then throw your trash. You know, just like those tourists that go to national parks and just, you know, destroy them. And you know, we've pretty much behaved that way. You know, we didn't care much about the environment. We polluted it with industrial gases, and we are now facing potentially climate change and so forth. So we are sort of behaving in a way, just taking advantage of whatever nature gives us around us. And but you can imagine civilizations that are trying to modify their environment to their benefit and use the best they out of it. But you can imagine the highest level of civilizations would be the ones that can recreate their environment. Just to give you an example, the sun is a nuclear furnace. It's a nuclear reactor held by gravity. And of course, you can imagine creating fusion in the laboratory and creating an artificial star, which is something that we managed to start doing actually just last year at the Livermore National Lab by shining lasers. It was possible to compress a pellet made of isotopes of hydrogen and create nuclear fusion there, something that nature does for us for free at the sun. But the highest level of civilization that I can imagine is the one that is able to create a baby universe. So this is a big challenge because you have to understand how the Big Bang started. And for that, you need the theory that unifies quantum mechanics and gravity. We don't have that. But just imagine a civilization that existed much longer than we did, and we had only the benefit of 1 century of science and technology. If they had 1,000 years, maybe 1,000,000 years, perhaps they would have a theory of quantum gravity, and then we'll be able to engineer a baby universe in the laboratory. So just think about it. If you are creating a whole universe out of nothing, you are recreating the environment that you live in, and that would be the highest level of civilization. And of course, in between those, where we are and where such a civilization may be, you can imagine a civilization that can create life, and just in the laboratory, create, the way biology does. So I suggest that the best way to gauge a civilization is whether it's able to recreate the environment that it lives in, not just use it for its own purposes.
Yeah, that's powerful. That's really incredible. You're talking about a civilization that can create an entire universe. There's, I think it was 15 college students that created a video game called No Man's Sky. It's 1 DVD, and on that DVD, there are 80 quadrillion planets, and the game never ends, and unlimited numbers of life forms that exist within that 1 DVD. and it's like, once you turn the game on, is that the Big Bang? And then because the game never ends, it's like they've created a fractal of what we live in right now. Do you believe in anything about the fractal holographic universe theory or idea or concept?
Well, so what was created on this DVD is a virtual reality. And, we know that, Mark Zuckerberg, for example, creates a virtual reality in the metaverse and sells it. And people put goggles on their head. And in the metaverse, they could become celebrities. They may live next to famous people. I have a problem with that because it's not the reality that we all share. I mean, basically, you are being sold a dream that has nothing to do with reality. And in fact, you can take recreational drugs and feel high and very good about yourself. But again, it will not represent the reality that we all share. And the problem I have with that is that it's not tangible. It's not something that everyone can use. It's just you enjoying that video game. And some people claim maybe we live in a video game, in a simulation. And I haven't seen any evidence for that. I haven't seen any pixels in the images that we see of reality. I haven't seen the simulation crash. So I prefer to believe that, we should take responsibility for the reality that we are. Because the one thing that if you live in a simulation or live in a virtual reality, you can say, who cares if I got a D in an exam? I could play it again, or maybe in the metaverse, in the multiverse, there is another copy of me that gets an A. So I shouldn't take responsibility. I think it's really not a good, it's a lazy proposition for someone to believe that we live in sort of a virtual reality. And if a plumber would come to my home and I would ask the plumber to fix the toilet or to fix the pipes, I would be very disappointed if the plumber would say, please put a some goggles on your head, and in the metaverse I fix all your problems. So that's my approach. Maybe I'm old-fashioned in the sense that I really care about reality, because the one reason I care about reality is because it comes to haunt you eventually. I mean, all of us will die, and if we don't do the right things, we could starve. Reality comes to bite you if you don't pay attention to it. And if you, for example, if you want to reach the stars, if you want to explore space, you better understand that the Earth moves around the sun. You can't live in a virtual reality where the Earth is at the center of the world, because that's not the reality. And if you were to send the spacecraft, they will never reach the destination if you think that Mars moves around the Earth instead of Mars orbiting the sun. So it's really important, if you want to adapt to the reality so that you can accomplish challenges, accomplish your wish. For example, Earth, eventually will not be habitable, because the sun will burn up all the oceans on Earth, and the Earth will become a desert, just like Mars, and we will need to move somewhere. And if you imagine all people putting goggles on their head and living in a virtual reality, and then the sun burning up Earth, nothing will survive, nothing will be left. So I feel responsible for attending to the reality, that, like, looking at the evidence, trying to collect it. Of course, it's constraining. It's not flattering. When you look at the mirror, you don't always look your best. You might find pimples on your face, but that's the reality. If you put makeup on your pimples, it doesn't mean that they went away. It just means that you are ignoring them.
Right, exactly. You got a good point there. And, that's funny. Stephen Hawking had a theory on black holes, and I know you study black holes as well. And then he came up with a new concept or theory about Hawking's radiation. Do you share that same theory, that black holes eventually evaporate?
Yeah, so that is a result of the fact that, a black hole is a prison. You can check in and you can never check out, according to, the theory of gravity that was formulated by Einstein about 110 years ago. So it's the ultimate prison. However, if you imagine, let's say, a person that is, or not a person, but a particle that is bigger than the size of the black hole. The black hole has a size because only inside of a certain region you can't escape. The escape speed is the speed of light. You can figure it out simply. From Earth, you can escape if you move faster than 11 kilometers per second. That's the speed by which rockets escape from Earth. If you were to take, I just wrote an essay where if you consider a mile-sized asteroid, a rock, from a rock of this size, gravity is so weak that even the tiniest frog can jump off the surface and become an astronaut. Just think about it. And the world record in high jump allows a person to escape from a rock that is the size of Boston or Manhattan Island. But from Earth, you need a spacecraft, you need a rocket to take you away from Earth. And from a black hole, nothing can get you out of. Basically, gravity is so strong that it even keeps radiation trapped inside of it. And there is a region around the black hole where nothing can escape from. It's called the event horizon. And the point is that if you have a particle that is bigger than the size of that event horizon, the particle is never confined, so it could escape. So imagine radiation with a wavelength bigger than the size of that horizon. It can escape. And what Hawking realized is that, in fact, all the time there are particles escaping from a black hole, and it evaporates, and eventually it loses energy until it shrinks and explodes. Basically, all the mass that it carried is evaporating from it as a result. And that was an amazing insight that Stephen Hawking had half a century ago, 50 years ago. Now, in my book, Interstellar, I talk about Hawking in a different way because, he was not able, he had a disease that disabled him from moving muscles in his body. At the end of his life, he couldn't move any muscle except his eyebrows and his cheeks. And he
Yeah.
had a machine that would read the motion of his eyebrows and translate them to words, to sentences.
Hmm.
He was at my home in about 7 years ago.
Wow.
And I call that the Hawking limit, where, I mean, he looked human. He would, at the end of an event, he would say, let's go to the bar and have some fun, and
Yeah.
he had an affair with his caretaker a decade ago. And so he was very much human, but it's human in the limit of your body not able to function. And I call that the Hawking limit, because in principle, I can imagine in a decade an artificial intelligence system that would imitate the mental states that Hawking had without moving any muscle. And that I call the Hawking limit. So what makes us human? It's not, I mean, we tend to think that it's our body that can interact with other human bodies, but no, it's actually your mental states. And that's what defined Hawking at the end of his life. He was a human by all definitions, but his body was not responding to his will. And so I really admired him in that sense, that he was a hero of science with a huge disability. And he was always an optimist. He was never depressed. When you interacted with him, he was always hopeful. And to me, I mean, how can anyone complain about life? If you are able to move around, you should feel lucky. And that sense of optimism was inspiring.
Yeah, no doubt. My mother, unfortunately, had the same exact illness, ALS, Lou Gehrig's disease. And so it's a very debilitating illness. He survived much longer than anyone else that I've ever known. And I attribute that to the power of his mind, possibly, because, man, his mind was just so powerful. One of the things that people tend to ask a lot, or not ask, they make comments when I talk about black holes on my social media and some of my lectures, saying that you can't talk about black holes because there's no evidence that they actually exist. No evidence. There's no evidence of black holes. Can you talk about the evidence that we know of black holes actually existing?
Yeah, so the best evidence was actually collected over the past decade. And it came in two ways. By the way, I was the founding director of the Black Hole Initiative at Harvard University that brings together astronomers, physicists, mathematicians, and philosophers who are interested in black holes. And just around the time when we started, there was a signal detected from the edge of the universe in the form of gravitational waves from the collision of two black holes. And what is this signal? Well, if you imagine throwing a rock to a pond, on the surface of the pond, you excite waves. We see those expanding from the place where the rock hit the surface of the water, right? We are all familiar with that. Now, according to Albert Einstein, his theory of gravity from 1915, space and time are not rigid. They are responding to matter. And gravity is basically curvature of space and time in the presence of matter. So matter tells space and time how to curve. And then the curvature of space-time tells matter how to move. That's basically the principles of Einstein's theory of gravity. Now, according to that, if you have a black hole, which is basically a mass concentrated to a point, so the solution to Einstein's equations of gravity, the first solution was derived just a few months after Einstein posted his theory in November 1915. So a few months later, Karl Schwarzschild, who was fighting for the Germans in the First World War, derived the solution to Einstein's equations for a point mass, a concentrating mass in a point, which ended up being the first solution of a black hole. And he derived that there is a region around it that is called the event horizon, from where nothing can escape, not even light. And when you take two such objects, which are the simplest that nature can give you, because you put all the mass at a point and you let these two black holes move around each other until they eventually collide, what happens is that because they move around, the distortion of space and time that each of them creates is now changing in time. It's sort of like moving, a stick in the water. You move it around and you continue to create waves. So in this way, the two black holes moving around, they create waves in space and time. These are called gravitational waves. And when they finally collide, you get a big distortion of space and time. That's the biggest you can imagine, because you have all the mass concentrated at the point for the two of them. And so when they merge together to make a bigger black hole, they create sort of a huge signal. And we can detect, using the LIGO experiment, which is made of lasers, we can detect those distortions in space and time, because when the wave passes through Earth, it basically shifts mirrors in the LIGO experiment in a way that the distance between the mirrors slightly changes because of the passage of those waves. And we can measure that. And that was discovered in 2015, exactly 100 years after Einstein formulated his theory. Wow. I'm sure he would have been delighted to realize that this prediction is validated. So what it confirmed are two things: that gravitational waves exist because we detected them, and moreover, that this messenger, the gravitational waves, told us that two black holes came together, because the signal that we measured is exactly consistent. It's in agreement with what you expect when two black holes come together. So that was an amazing triumph to Einstein's theory of gravity that confirmed both the existence of gravitational waves as well as black holes. But a few years later, in 2019, an image of a black hole was obtained, actually at the conference room of the Black Hole Initiative that I founded. And we now have an image which looks like a shadow. So basically what the image is, we're talking about a black hole in a nearby galaxy that has a black hole of about 6 billion suns. So just imagine matter that weighs as much as 6 billion times the mass of the sun came together to make such a huge, giant black hole at the center of a galaxy called M87. And it casts a shadow on the light that is emitted from hot gas that is falling into it. So the gas is shining, and then you see a region which is dark, which is basically the shadow of the black hole blocking the light. I mean, it's not really blocking, it's absorbing the light coming from behind it. And you see a beautiful shadow, a dark region, silhouette, surrounded by a ring of light. And the ring of light is because the black hole bends light that goes around it and focuses it, just like it's called the gravitational lens, just like a lens. And what you end up with is a sort of a ring that looks like a sliver of the moon, basically, light. And this image, when it was obtained back in 2019, appeared on all major newspapers. And so that's the other direct evidence we have for a black hole, this time a very massive one in M87. The previous, the gravitational waves that were detected by the LIGO experiment, they were indicating black holes that result from the collapse of massive stars, tens of times the mass of the sun. So we know that there are black holes of very different masses, starting from the masses of stars. When stars die and the cores collapse for massive stars, they end up in a black hole. And also very massive black holes that exist at the centers of galaxies. In fact, the Milky Way galaxy has a black hole of 4 million times the mass of the sun. And that was imaged as well a few years ago, in addition to M87. So these are the most direct clues that black holes exist. But we also knew for decades from a variety of indirect measurements that black holes exist, because there were objects that were just too compact and were emitting a huge amount of light that otherwise you would not get from any reasonable source.
Right. Incredible. Thank you for bringing the evidence, because a lot of people, like I said, sometimes you can be a conspiracy fanatic. It's okay to be, and it's healthy to be a conspiracy theorist and to consider and ponder things and ask questions. but sometimes you can be a fanatic where you take, this is what you're talking about now is real peer-reviewed science. And I think it's important for people to take that information and weigh it against their judgments and their personal feelings about things. Because like I said, when I talk about black holes, I see a lot of comments about black holes, there's no evidence of them, but you clearly, eloquently just showed us that there is evidence of black holes. And yes, they do exist. And yes, we even know the mass of these black holes.
And we can embark on a journey. If anyone wants to go to a black hole at the center of the Milky Way, I mean, it will take a while, but I wouldn't advise it, because once you get there, your body would be ripped apart when you get close to the center. I mean, but if you want, if you have a terminal disease, or you just want to have an amazing experience, just going into one of the nearby black holes.
Right. Now, what's interesting about the black holes, there seems to be this other theory, it's kind of interesting to think about. Could a black hole create a white hole? Maybe two membranes touching each other in membrane theory, and then creating a white hole on the other side. And the energy that's getting sucked in from the black hole is now being energy spewed into another universe. What are your thoughts on that?
Yeah, so let me explain what a white hole is. So according to Einstein's theory, a black hole is when matter falls in and ends up at a point. Okay, so that's easy to understand. You just, for example, a star, once it consumes its nuclear fuel, there is nothing to support it against collapse. There is no source of energy to support it against the collapse. Usually what supports the sun is the pressure, the energy created in the middle that is pushing the gas out and balancing gravity. But once the fuel is exhausted, there is no more energy source in the middle, and then the star just cools and collapses, shrinks, and it could, if it's massive enough, gravity is strong enough to bring it to a point, making a black hole. That's easy to understand, and it happens in nature. We know of those stellar mass black holes, like the ones detected by the LIGO experiment when the two collided at the edge of the universe. Okay. Now, a white hole is an idea that says, if you look at the equations that Einstein formulated, you can reverse the direction of time. So instead of matter falling in to make a black hole, now let's reverse the direction of time. That's also, in principle, a viable solution to the equations, because the equations allow for time reversal. So now what you have is a point from where energy is spewing out, coming out. Matter is coming out. Now, the problem with that is, what do you start from? I mean, where is the energy coming from? You have to imagine a situation where there is an infinite resource of energy somewhere, and it keeps spewing it out. And the problem with that is really that there is no well-defined initial state that you can start from, where you say, okay, I arrange a system that I know about. I know about stars, I know about planets, I know about the universe. You arrange a system. Here, you need to arrange a system that has an infinite reservoir of energy, somehow spewing it out. And that is not a valid set of initial conditions. And moreover, it affects the rest of the universe. So you don't know what to start from, and yet it affects the rest of the universe. That's a very problematic solution in physics, when you have an effect on the entire universe from a system, in this case the white hole, for which you don't have an initial state. You don't know how to make it. And that's why this leads nowhere. I mean, in the context of Einstein's gravity, I mean, people knew about white holes, but pretty much ignore them, because it's not a well-defined initial, you can't really create it from a set of initial conditions. People speculated, okay, maybe, as you said, maybe if you make a black hole, then matter can go through the singularity at the center of a black hole, through some wormhole into a white hole. But that's a complete speculation. We don't know if. So, in fact, most physicists, if you ask them, would say, a white hole is not really a viable thing to consider, because you can't create it from anything we know. Okay, and that's why it's being ignored now. Carlo Rovelli wrote a book about white holes. Now he works. He just published it a month ago or so, and he works on trying to unify quantum mechanics and gravity, and is speculating about the existence of white holes. I would call it a speculation, and I would still argue that it's still a very problematic concept to even discuss, because we don't know how to make it in the first place. And he would admit that. So I would say let's ignore it for now, because it's really not a well-defined concept in the way that we are used to. I mean, there is no free lunch in nature. You can't just get an infinite amount of energy from nothing.
Right, exactly. Well, it's just, it's another thing to ponder and question and think about. But obviously, we know so little about the universe. And so, like you said, a lot of this is speculation and theory.
Right.
One other thing I want to touch on black holes before I move on was I heard some scientists, some quantum theoretical physicists talking about the fact that everything entering across the event horizon, even though it's pulled apart, the information or the data is somehow stored in the region around the black hole.
That's true.
What are your thoughts on that?
Yeah, so just to give you an example, if we consider the black hole at the center of the Milky Way, that's a giant black hole of 4 million times the mass of the sun. If you are an astronaut and you are just crossing the event horizon of that black hole, after you cross it, you will not be able to send any DMs, any text messages to your friends, because you are inside the prison. That's the ultimate prison. You can't really communicate from inside, but nothing bad will happen to you, because that's the size of this black hole is about a tenth of the Earth-Sun separation. It's a huge region. And once you enter into that region, your body would not be ripped apart. That the tidal force between your toes and your head, will not be. You will not feel it. You will just go there, and nothing unusual will happen to you. So obviously, you are still a thinking person once you enter such a gigantic black hole. So even though you can't communicate anything to the outside world, the information in your brain and everything you see around you is still in there. Now, eventually, you will get to the so-called singularity at the center of the black hole. That will take a few hours, and then you will be there. And then the question is, what happens to you there? So we don't know, because what happens is Einstein's theory breaks down. Because we don't have a unified theory of quantum mechanics and gravity. Once you reach the singularity, we don't know what happens to you. Quantum mechanics starts to play a role, and we don't have that theory, so we don't know what will happen. My personal belief is that there might be an object near the center of a black hole that has the maximum possible density that any object can have. It's called the Planck density. And it sits there, and when you reach that object, you're added to it. You just collide with its surface and added to it. And the reason I thought about it is because one day my basement, the basement of my home, was flooded, and I invited the plumber, and I realized, usually the water just goes out through the sewer. But some tree roots were blocking it, and so water was accumulating in my basement. And so, one theory, as we were discussing before, is that at the center of a black hole, the situation is similar. Maybe matter goes through the center into a white hole on the other side, into something but maybe also it's just stuck there and keeps accumulating in an object. So I would prefer the notion where we just have an object at the center of a black hole. We don't know what it is exactly, because we don't have a theory of quantum gravity, but the information is in there. You don't lose it. It's just like, if you throw a book into the sun, the information, the book will be burned, but in principle, the information is encoded in the radiation that the sun emits.
Exactly. Oh, what a powerful way to say it. That's incredible. We're going to pivot a little bit to something that you've talked about quite a bit that really got you critically acclaimed worldwide. And I really believe in your theory about this. The Oumuamua object that came through our solar system, which was it was just huge. Well, it wasn't too big, but it was pretty big. this object that came, this interstellar visitor that came through our solar system and then went around the sun almost like a gravitational assist in a weird kind of way and shot back out into the galaxy. Can you elaborate on that a little bit?
Right. So, for 70 years or so, we've been trying to search for other intelligent civilizations out there to answer the question, are we alone? And we were doing it by trying to detect radio waves, radio signals. And that's just like waiting at home for a phone call. Maybe nobody would call you when you're waiting. A different approach would be to search for objects in your backyard, because maybe one of them would be a tennis ball thrown by a neighbor, and instead of the rocks that you are familiar with. So it turns out that we haven't yet, we haven't detected objects from outside the solar system close to Earth until the last decade. So in 2017, the first report came along from a telescope in Hawaii. It was about an object the size of a football field, given the name Oumuamua, which means a scout in the Hawaiian language. And this object was really strange, didn't look like the rocks that we are familiar with. It had a very extreme shape, most likely flat, based on the reflection of sunlight. As it was tumbling every 8 hours, the amount of sunlight reflected from it changed by a factor of 10. And it was also pushed away from the sun by some mysterious force without any evaporation. There was no gas emitted from it, no rocket effect. It didn't look like a comet. And so I suggested maybe it's being pushed by reflecting sunlight. That's all. And it behaves like a sail, very thin membrane being pushed by reflecting sunlight. These are called the light sails. You can imagine it being the surface layer of a bigger object or a broken piece of a bigger object. At any event, I suggested maybe it's an artificial object made by another civilization, not something natural, because it looked so different from a rock. And then we discovered with my student, Amir Siraj, we discovered that 4 years earlier, there was a smaller object, roughly the size of a watermelon, that collided with Earth at a very high speed. And it came from outside the solar system because it was not bound by gravity to the sun, just like Oumuamua was moving too fast to be bound to the sun. This one was a meteor detected by US government satellites, and it had an unusual material strength. It was tougher than all the space rocks cataloged by NASA over the past decade, because it maintained its integrity down to the lower atmosphere, and moreover, was moving very fast. So I said, well, maybe it's a Voyager-like meteor. Imagine our own Voyager colliding with another planet like the Earth in the distant future. It would appear as a meteor in the sky of that planet, of unusual material strength because it's made of an artificial alloy, and unusual speed because it was propelled by a chemical rocket. And so I decided to lead an expedition to the Pacific Ocean this summer in June 2023 to search for the materials of this object. And amazingly, we found materials that are of composition that was never seen in the solar system, that maybe indeed confirming the fact that this object came from outside the solar system. And we are now finishing the analysis this month of all the materials we recovered at the meteor site. And that was a very challenging task because it was in the Pacific Ocean. The ocean is about 1 mile deep, and the region was 7 miles in size. And we were looking for tiny droplets left over from this object, the size of a grain of sand. We found almost 800 of them.
Wow, that is amazing. I heard about it. It was on the news. It made international news. And I heard that you were going on this expedition. And I'm glad you were able to find some remnants of this. You think it's metal? Is it metallic in nature?
Yeah.
What type of elements are in there?
It's mostly iron, but it has a very high abundance of rare elements like uranium, lanthanum, beryllium. And so we're still analyzing, but some of those molten droplets are really unusual, never seen before. And it's quite amazing that we were able to find them.
Yeah.
And, obviously, a lot of people said you will not find anything. It's really difficult. And I realize that life sometimes is a self-fulfilling prophecy. So it's better to be an optimist. If we would not search, we would not find anything.
Exactly. I mean, you know, you have to go after your passion, and that seems like exactly what you're living. You're living in your passion, and that's why you're having so much success. One of the first elements on the periodic table is hydrogen. When from my studies, it appears that we try to communicate on the hydrogen frequency with other potential advanced civilizations. Have you seen any evidence of anything coming towards us, or any interactive communication, or any energy beams in that frequency?
Yeah, so this is a very popular frequency for astronomers because we often search for hydrogen, for example, in the Milky Way galaxy or farther away. In fact, for the last 2 decades, I pioneered one of the most important frontiers of research in astrophysics, which is to map the hydrogen in the universe all the way back to when the universe was only a few percent of its present age, using hydrogen, exactly the frequency that you were talking about. There are now a number of observatories being built to search for that and map the hydrogen in the universe. And that can tell us about the beginnings, when the first stars formed and out of that hydrogen, because they produced radiation that destroyed the hydrogen. And we could see initially that there was lots of hydrogen, and then eventually it was broken up to electrons and protons by the light coming from the stars. That is a process that we very much want to map in the universe. So that's one of the frontiers right now in cosmology. I started working on it 2 decades ago, and back then it was not that popular. So as you are saying, of course, civilizations could potentially choose that frequency of hydrogen to be close to it, because they may realize that other civilizations may actually monitor the sky at this frequency, and therefore if you wanted to communicate with them, that would be a good place to be, because they would develop radio telescopes to search for that frequency. And so far, we haven't seen anything unusual at that frequency, but maybe we will.
Right. It's pretty incredible. And analyzing the sky in that way, one of the things I know you also study and research is dark matter and dark energy. Have we come close to any kind of a theory or idea as to what is exactly creating this dark matter and dark energy and creating this expansion?
Yeah, this is an amazing topic, because about 80 years ago, an astronomer named Fritz Zwicky realized that most of the matter in the universe is not visible. It's invisible. And the reason you know about it is because you see that there is much more gravity than you can assign to known forms of matter. You realize that clusters of galaxies, which are groups of galaxies like the Milky Way, they would break apart given the speeds of those galaxies, unless there was some invisible matter keeping them together. So he assumed that there is more mass than the eye can see, and called it invisible matter, or now we call it dark matter. Yeah. And at first, people just ignored it. Astronomers ignored it. But then after about 40 years, it became very popular. And now we have very clear evidence that 83% of the matter in the universe is from a substance that we've never witnessed in the solar system. We've never detected it. So we don't know what it is. It could be an elementary particle that is interacting with light very weakly, so we can't see it. It doesn't emit light, it doesn't absorb light. Or it could be maybe black holes, primordial black holes that were made after the Big Bang, that also are dark, and they're tiny, and maybe the mass of an asteroid or a planet. So we can't really easily detect their existence. And so there are all kinds of possibilities. We don't have a clue. A lot of money was invested in searching for the dark matter, most recently in the Large Hadron Collider at CERN, and people were hoping to find to produce the dark matter particle by smashing protons and nuclei against each other at very high energies, but nothing new was found. So we are still in the dark about the dark matter. But then, about 2 decades ago, 25 years ago, it was discovered that there is another substance that we don't know, and that actually amounts to more in the mass budget of the universe right now, and that is called dark energy, which is pretty much the energy of the vacuum. If you remove all the matter, whatever remains is the vacuum, and the vacuum may not be empty. And it turns out that it needs to have a significant mass per unit volume. So because we see the universe expanding, but the expansion is accelerating over time, it's getting faster and faster. And that is predicted by Einstein's theory of gravity. If the vacuum has some mass per unit volume, it produces negative gravity, basically repulsive gravity. What happens is, as the universe expands, at early times, matter is very dense, so it dominates the mass budget per unit volume. But then as the universe expands, matter gets diluted, and the vacuum doesn't change, it remains the same. So at some point in time, when the universe was half of its present age, that's when matter was diluted enough for the vacuum to start dominating the cosmic expansion. And since then, we see the universe accelerating. So that was a discovery that actually 2 graduate students at Harvard were responsible to, and received the Nobel Prize. And when I arrived to Harvard University, there were students, and one of them took my class in cosmology. And he told me later on, after getting the Nobel Prize, he said, "Avi, I didn't tell you that, but actually it's thanks to you that I worked on this subject, because in your class on cosmology, you said that we can infer the expansion rate of the universe by measuring distance of objects, if they are standard candles, if you know how much light they produce, then you can infer how far they are based on how faint they look to you." And so he realized that you can use supernova, exploding stars, for that purpose. That was Adam Rees, and told me that he came to this idea as a result of attending my class as a graduate student. So I felt quite flattered that at least one of my students listened to what I said.
Oh, that's incredible. So you sparked the mind. And that's really what all this is about. This is about sparking the mind and giving people a little bit of light that they can then follow that light and see what it illuminates in their own consciousness, in their own experiments, or in their own research. And it takes everyone on a journey. So every time you come up with these theories, ideas, the teachings that you put out, the information that you've learned scientifically, and then you continue to pass that information on, people take it, and then it just sparks them, and they begin to find their own way and find their own highway in life. And you've probably inspired by now, I'm sure, thousands, maybe even tens of thousands of incredible scientists and researchers around the world.
I'm very grateful for that, and because, in a few decades, I will not be around anymore. And perhaps these ideas would outlast me and survive around. So that gives me a lot of satisfaction, actually.
Yeah, it's a form of immortality in a way,
Exactly. Exactly.
Which is incredible. Yeah, it's the universe passing the knowledge on, because I really do believe that we're like a fractal of the universe. In other words, the universe itself as a whole on the large scale is part of what's inside of us, and we're acting that same role out in a weird kind of way, on a smaller scale, and we're just passing down all this information.
Right.
I know you mentioned artificial intelligence earlier and how its effect is going to change the way intelligence is on this planet. How do you see artificial intelligence and machine learning shaping the future of astronomical research?
Oh, I think it's extremely important. And in fact, the news from OpenAI over the past week, where there was some kind of an incident there where Sam Altman was kicked out and then brought back in. That may have been triggered by the realization that, we're getting to a point where GPT, I mean, the large language models would be able to address problems that they are not trained on, that, they will start to show ingenuity, similar to the way a scientist works. Like if you face new data, new circumstances, you can come up with a novel idea that explains that data. And if that will be the case, then we can use, obviously, AI for science. There will be AI scientists, and that could propel us to new knowledge, which is very important, because in science, part of the reason that we don't make progress as fast as we could is because of human weaknesses, that people are too conservative. They're not daring to take risks.
Yeah.
They are attached to their own ego, and in that way suppress new knowledge because it threatens what they already know, what they already talked about. And however, a machine may not have those traits, and that could help us as long as it's sufficiently intelligent. And I'm very proud of our technological kids. I'm not worried about them. It's just the same way that I'm really hopeful that we will find a higher intelligence in interstellar space, that we could learn from, because it's an opportunity for us to grow. As when I was jogging on the deck of the ship on the Pacific Ocean one morning, I usually jog at sunrise. I do it on land, and I did it there. And there was a filming crew, 1 out of 50, that wanted to be there. And the director asked me if they can film me jogging that morning. And they asked me to jog for about 10 miles instead of the usual routine. And so so then at the end of it, the director said, Avi, it looks like you are running. Are you running away from something or towards something? And I said both. I'm running away from some of my colleagues in academia who have very strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space.
Nice.
So altogether, for me, the real hope is that we will use AI in space, because when you travel large distances, there is no way for the probe to wait for guidance from the sender, because it takes a long time. It takes thousands of years for signals propagating at the speed of light to cross the Milky Way galaxy. So it needs to have its own brain, make its own decisions, and artificial intelligence is the best way to do it. We haven't sent AI astronauts. We haven't sent probes with their own artificial intelligence as of yet, but maybe within the coming decades, we will do that.
Yes, that would be so great. And sir, thank you for being on here today. Are there any other new projects you wanted to tell everyone about? Anything you have coming up?
Yeah, we are planning the next expedition. We have an observatory at Harvard University monitoring the sky for unidentified anomalous phenomena. And obviously, we'll report back to the public if we see anything unusual, like a probe from another civilization. One thing I wanted to close with is to tell all the young people in the audience, or maybe even the older as well, never pretend to be the adult in the room. Maintain your childhood curiosity, because I often worry, that the childlike bullying is much more prevalent, especially on social media, than childlike curiosity. And I try to remain the kid that I always was, and I'm proud of that. I could make mistakes, but there is nothing better than following your curiosity, because you always learn something new from everything, from any person you speak with. So stay humble. Don't pretend that you know more than you actually know.
Yes, so powerful. Everyone, Avi Loeb. Avi, thank you for coming on the podcast. I appreciate you so much, and we'll make sure you get a copy of this video as well.
Thank you so much for having me.